Welcome to Multivariate Calculus. Today we are going to explore a fascinating topic, cylindrical and spherical coordinates. Have you ever tried to describe the shape of a pipe or a planet using a standard rectangular grid? It gets incredibly messy very quickly. By the end of this video, you will understand how changing our mathematical perspective to match the natural symmetry of an object can turn impossible calculus problems into simple, elegant solutions. Let us dive in. Let us start by imagining you are standing in a circular room and need to describe the exact location of a fly hovering in the air. Using standard Cartesian coordinates means measuring how far forward, how far left, and how high the fly is. But in a circular room, it is much more natural to just point at the fly, measure the angle of your arm, measure the horizontal distance to the spot directly under the fly, and then measure straight up. This is exactly what cylindrical coordinates do. They take the familiar two-dimensional polar coordinates, a radius and an angle, and simply add a vertical height. This system is incredibly useful when dealing with objects that have a central axis of symmetry, like pipes or wires. Now that we understand what cylindrical coordinates are, let us look at how to convert them back to our standard grid. Conceptually, we are just finding the projections of the shadow on the flat ground. The symbol r represents the distance along the ground, measured in units of length. The symbol theta represents the angle of rotation, measured in radians. By multiplying the distance by the cosine of the angle, we find the exact projection onto the primary horizontal axis, giving us x. Using the sine function gives us the secondary axis, y. As the angle changes, these projections smoothly oscillate. Finally, the vertical height z remains exactly the same in both systems. If you increase r, the point moves further from the center pillar. If you increase theta, it orbits around the center. Before we move on, let us see this with a concrete example. We are given the Cartesian coordinates of a point in space. Specifically, x equals 1, y equals the square root of 3, and z equals 5. Our goal is to translate this exact location into the cylindrical coordinate system. Why choose this approach? Because finding the radius and angle will give us a much more intuitive sense of where this point lies relative to the center. We will first calculate the radial distance using the Pythagorean theorem, which calculates the straight line distance from the origin to the point's shadow on the flat ground. By substituting our given x and y values, we square 1 and the square root of 3, adding them to get 4. The square root of 4 gives us a clean, perfect radius of 2. Continuing with our conversion, we have successfully found the radial distance. Next, we need to find the angle that tells us how far to rotate around that central vertical axis. We use the tangent relationship for this step, which relates the angle to the ratio of the y and x coordinates. Plugging in our known values, we get a tangent value of the square root of 3. In trigonometry, we know that this specific value corresponds to an angle of pi over 3 radians in the first quadrant. The vertical height z was given as 5 and does not change. Therefore, our final cylindrical coordinates tell us a physical story. Walk out 2 units from the center, turn pi over 3 radians and climb straight up 5 units. Now that we have used the basic coordinates, let us understand how to calculate volumes. When we integrate to find volume, we chop space into tiny pieces called volume elements. In standard coordinates, this is just a tiny rectangular box. But in cylindrical coordinates, the box is actually a curved wedge. As you move further away from the center, meaning as the radius increases, the wedge gets wider and wider. To account for this stretching, we must multiply by a mathematical correction factor, which is simply the radius r. The symbol dv represents this tiny volume. If you forget to include this r, your calculations will assume the wedges are the same size everywhere, which is physically incorrect. Increasing r physically stretches the outer edge of our tiny volume wedge. This brings us to our next major system, spherical coordinates. Imagine you are an air traffic controller tracking an airplane on a radar screen. The radar dish does not measure a grid position, nor does it measure a flat circle and a height. Instead, the dish points directly at the airplane. It measures the straight line distance from the dish to the plane, the compass direction the dish is facing, and the angle the dish is tilted up into the sky. This is the essence of spherical coordinates. It is a system based entirely on one distance and two angles. Why does this matter? Because it is perfectly suited for anything radiating outward from a single central point, like light from a bulb, gravity from a planet, or sound from an explosion. Let us visualize exactly what we just described. Here, you are seeing the three-dimensional axes, x, y, and z. Look at the point P floating in space. The solid line connecting the origin to point P represents our first variable, rho, the straight line distance. Now, notice the angle labeled phi at the top. This is the polar angle, measuring how far we tilt down from the vertical z-axis. Finally, look at the dashed shadow on the flat ground. The angle theta sweeps from the x-axis to this shadow, acting exactly like a compass heading. This diagram teaches us that spherical coordinates are just two connected right triangles, one standing up vertically and one lying flat on the ground. Now that we can visualize the geometry, let us look at the formulas that connect spherical coordinates to our standard grid. Conceptually, these come directly from the two right triangles we just saw. The vertical height z is simply the adjacent side of the vertical triangle, found using rho times the cosine of phi. The shadow on the ground has a length of rho times the sine of phi. We then project that shadow onto the x and y axes using cosine and sine of theta, just like we did in cylindrical coordinates. The symbol rho is a distance, measured in meters. The symbols phi and theta are angles in radians. If you increase phi, the point physically drops lower toward the ground. If you increase rho, the point shoots further out into space. This brings us to the most important formula to remember when doing calculus with spheres, the spherical volume element. Just like the cylindrical wedge, a spherical wedge gets larger as you move away from the center. But here, it grows in two different directions. It gets wider as the distance rho increases, and its horizontal width changes depending on how far down it is tilted. The mathematical correction factor works out to be rho squared times the sine of phi. The symbol dV is the tiny volume. Rho squared accounts for the wedge getting wider as you move outward. The sine of phi accounts for the wedge getting thinner near the poles and fatter near the equator. If you increase rho, the volume element physically expands. You must multiply by this factor every single time you integrate. Before we move on, let us see this with a concrete example. Our task is to calculate the total volume of a perfectly round solid sphere of radius r centered at the origin. What is given is the shape and radius, and we are asked to find the total volume. Why choose spherical coordinates? If we tried standard Cartesian coordinates, the boundaries would involve complicated square roots that make integration a nightmare. By using spherical coordinates, the curved boundaries become simple, constant numbers. We start with the general triple integral for volume. We replace dV with our spherical volume element. The limits perfectly describe a solid sphere. The distance rho goes from 0 to r, the polar angle phi goes from 0 to pi at the south pole, and theta sweeps a full circle from 0 to 2 pi. Continuing with our calculation, we begin by evaluating the innermost integral, which is with respect to the radial distance rho. During this step, we treat the angle variables as if they were constant numbers. The antiderivative of rho squared is rho cubed over 3. Evaluating this from 0 to r gives us a simple algebraic fraction, r cubed over 3. Next, we move to the middle integral, which deals with the polar angle phi. We bring down the result from the previous step and multiply it by the sine of phi. The antiderivative of sine is negative cosine. We set up our evaluation brackets from the upper limit pi to the lower limit 0. We are systematically collapsing the three-dimensional space down, one dimension at a time. Let us carefully plug the boundary values into our negative cosine function. The cosine of pi is -1 and the cosine of 0 is +1. Subtracting these values carefully accounts for the double negatives, resulting in a simple integer, 2. This integer multiplies our previous fraction, giving us 2r³ as the accumulated value so far. We have now reduced the complex triple integral down to a simple, very simple integral. The remaining variable is the azimuthal angle theta, which represents the full rotation around the vertical axis. Notice that our integrand is now just a constant number, containing no theta variables at all. This makes the final integration step incredibly easy to perform. For our final step, because we are integrating a constant over an interval, we simply multiply the constant by the length of that interval. The interval length is 2 pi, representing a full 360-degree rotation. Multiplying our constant by 2 pi yields the final famous geometric formula for the volume of a sphere. This proves mathematically why the volume of a sphere is exactly 4/3 pi times the radius cubed. Physically, this final answer represents the total amount of three-dimensional space enclosed within the spherical boundary. By aligning our mathematics with the natural symmetry of the shape, we turned a nearly impossible Cartesian problem into a straightforward sequence of basic integrals. Now that we have seen the math in action, why does all of this matter? In the real world, very few things are perfectly shaped like rectangular boxes. Planets, stars, electromagnetic fields, and fluid flows in pipes all possess natural curves and symmetries. If an engineer tries to model the heat distribution inside a nuclear reactor core using a standard grid, the math becomes overwhelmingly complex and prone to errors. By switching to cylindrical or spherical coordinates, the mathematics aligns perfectly with the physical geometry of the object. This alignment simplifies the equations drastically, allowing computers to simulate weather patterns, design aerodynamic rockets, and map the gravitational pull of black holes with incredible precision. Choosing the right coordinate system is half the battle in physics. We have covered a lot of ground today, so let us reinforce the most important ideas. First, cylindrical coordinates adapt our perspective for tube-like structures by adding a vertical height to a flat circular grid. Second, spherical coordinates pinpoint locations using a distance and two angles, making them ideal for round, radiating objects. Third, and most crucially, when integrating, you must always include the mathematical correction factors for the volume elements to account for the stretching of space. You have now covered the full topic of cylindrical and spherical coordinates. Mastering these systems is the key to unlocking advanced physics and engineering, turning complex curved boundaries into simple, manageable constants. Keep practicing, and the geometry will become second nature.